Logarithmic functions. Logarithmic functions are the inverse function of the exponential function. The function f of x is equal to log base b of x is a logarithmic function with a base of b. Y is equal to log base b of x and b to the y power equals x are two ways of expressing the same thing. So these two expressions are equal. Y is equal to log base b of x is the logarithmic form, and b to the y power equals x is the exponential form. If you'll notice, in both of these forms, b is called the base. So in the logarithmic form, the way that we read this is y is equal to log base b of x. And then, of course, in the exponential form, the big number is the base of the exponent, which is our power. Also, in the logarithmic form, this is log base b of x. Well, whatever that number is, that's called the argument of the logarithm. In order to write a logarithm in its equivalent exponential form, this is what we do. We take the base of the logarithm, so in this case our base is 7, and we raise it to this power, okay, so it's 7 raised to the 3 power, or the third power. So the exponent is what it's equal to, all right? And then it equals the argument. So it's just like we go in a little circle. We take the base, we raise it to what it's equal to, and then it equals the argument. Okay, so let's try it again. In B, all right, we have 2 is equal to log base b of 25. So again, we start with our base is b, and we raise it to the second power, and then it equals our argument, which is 25. Now C is written a little differently. They've just switched the sides. So we still start with our base. In this case, our base is 4, and we're going to raise it, or our exponent is going to be what it's equal to. So 4 to the y power equals the argument, which is 26. Now we're going to go in the opposite direction. This says to write each equation in its equivalent logarithmic form. All right, so we're starting with the exponential form. 2 to the 5th power equals x. So the base of our exponent is the base of our logarithm. So I'm going to start out writing log. And since the base of my exponent is 2, the base of my logarithm is 2. And again, we're going to go in a circle. So this is 2, and my argument is going to be x. So log base 2 of x is going to equal the exponent. All right, and it's written like that. Okay, for the next one, we have b to the 3rd power equals 27. So the base of my exponent is b, so the base of my logarithm is going to be b. So log base b, all right, so we're going to go in a circle, of 27 equals the exponent, so it equals 3. And then the last one, my base is e, so log base e of 33 equals y. And for any of these, if you wanted to write it the other way, say if you wanted to start with what it's equal to, start with a y equals log base e of 33. If you wanted to write it that way, it would be fine too. We're going to talk a little bit more about log base e in a minute. But for now, this is the way that we change an exponent into a logarithm. Now, if the directions say to evaluate, we're trying to figure out what this equals. So here we have log base 10 of 10. We want to know what this equals. So we don't know what it equals, so I'm going to put an X right here. So what we're saying is they're wanting to know what power can we raise the base to get the argument. So remember, if we were to write this in the exponential form, we're saying 10 to what power equals 10? All right, so if we can answer that question, that's going to be what our logarithm is equal to. Okay, so what power can we raise 10 to get 10? And we know that anything raised to the first power or raised to the 1 power equals itself. So this equals 1. All right, for B, we're saying what power can we raise 5 to get 1 over 125? Okay, so that one is a little tricky. So first of all, if I say, what power can I raise 5 to get 125, we know that that would be 3. 5 to the third power is 125. But our argument is not 125, it's 1 over 125. So if we remember our exponent rules, in order to flip our base, we have to raise it to a negative exponent. So this would just be negative 3. So if we rewrote this in our exponential form, just to kind of check it out, if I said 5 to the negative 3 power, what would that equal? Well, first of all, we would have to flip our base to make our exponent positive. And now we have 1/5 to the third power, which would equal 1 over 125. So we know that we did that right. Okay, for C, we have log base 36 of 6 equals what? So we're saying, what power can we raise 36 to get 6? So this time, instead of my number getting bigger, it's getting smaller. So can you think of what can we do to 36 to get 6? Well, I know if I take the square root of 36, I get 6. So how could we write that as an exponent? If I said 36 to what power equals 6? Okay, so if I want to take the square root of 36, the way that I write that as an exponent is 1/2. Remember, again, if we back up to our exponent rules, if we have a fraction for our exponent, this bottom number is the root of our exponent, and then the top number is the power. So if we have a fraction or rational exponent, the denominator is the index of our root. So if I want to take the square root, it would be 1/2. So that just means that 36 to the 1/2 power equals x. So if I write it as a logarithm, log base 36 of 6 equals 1/2. Logarithms have several different properties. The basic logarithmic properties involving 1 is this: log base b of b equals 1. All right, well that makes sense because we know that anything raised to the 1 power is itself. So we can just use this property. If we see this, anytime that our base and our argument are the same, we know that it's going to equal 1 because anything raised to the 1 power equals itself. All right, and then for the second logarithmic property involving 1, log base b of 1 equals 0. Well, we know that this is true because b, or anything raised to the 0 power, equals 1. So if we have a base and our argument is 1, so anytime our argument is 1, we know that the logarithm has to equal 0, because to get this to be 1, our base had to be raised to the 0 power. All right, so let's evaluate this. Log base 9 of 9, what does that equal? Okay, so we know that anytime these two things are the same, that's got to be 1. For b, log base 8 of 1 equals, and we know that it would be 0 because anytime this is 1, it has to equal 0. Okay, for inverse properties of logarithms, if we have log base b of b to the x power, that's going to equal x. This makes sense because b to the x power equals b to the x power. So to kind of shorten that, anytime these are my base, the base of my logarithm and my argument are the same, it's going to equal whatever that power is. This is pretty much the same thing as that logarithmic property involving 1. Let's back up. Because we're saying if these two things are the same, then it equals whatever the exponent is. Well, in this case, if we don't see an exponent, we know the exponent is understood to be 1. So this other property is basically the same thing, except for that power is not 1. So as long as the base and the argument are the same, it's going to equal whatever that power is. And if you don't see a power there, then it's 1. It's kind of the same thing when we're dealing with the exponential form. If the base of our exponent is raised to a log with the same base, then those two things just kind of cancel out and it equals whatever's left. So if you see things that look the same, whether it's a logarithmic form or an exponential form, so here this stuff look the same, it equals what's left. These two look the same, it equals what's left. So let's use those properties. Log base 7 of 7 to the 8 power. Okay, so this stuff that looks the same, it just kind of cancels out, and this is going to equal 8. 3 raised to the log base 3 of 17. Again, this stuff looks the same, so it cancels out, so this just equals 17. Now we're going to look at the graphs of exponential functions and logarithmic functions. These two functions, f of x is equal to 3 to the x power, and g of x is equal to log base 3 of x, are inverses of each other. Okay, so let's graph the f of x is equal to 3 to the x power. Remember, anytime we want to graph a function, all we have to do is create a t-table. So I'm going to create a t-table, and I'm just going to plug in these values. So negative 3 raised to the negative 2 power. Remember, to get rid of that negative, we flip the base, so we have 1/3 squared, which would be 1/9. Okay, and then 3 to the negative 1 power, that would be 1/3. 3 to the 0 power, anything to the 0 power is 1. 3 to the 1 power is 3, and 3 squared is 9. Okay, so if I plot these points on the graph like this, and I connect those points, this is what the graph of our exponential function looks like. And we did that in the last lesson. So that's what the exponent looks like. Now let's do the logarithm. Well, I don't know, I can't just look at the logarithmic form of the function and figure out how to graph it. So I'm going to change it to its equivalent exponential form. So remember the way that we change this to an exponent. We take the base, we raise it to this power, and it equals the argument. Okay, so I'm going to change the g of x to y. Okay, so 3 to the y power equals x. That would be the equivalent exponential form of this logarithm. So instead of plugging in values for x, let me plug in values for y. So I'm going to plug in the same values that I used for x in the previous function. All right, so if I do that, I'm doing the same thing. I'm doing 3 to the negative 2 power. We know that that's 1/9. 3 to the negative 1 power is 1/3. 3 to the 0 power is 1. 3 to the 1 power is 3. And 3 squared is 9. All right, so I'm going to graph this using blue. So if I plot these points, my graph doesn't go on my y-axis to 9. But anyway, these are most of the points. And if I connect these dots, this is what the graph looks like. And if you'll remember, any exponential function that we have, not exponential function, any inverse function that we have reflects across that imaginary y equals x line. And so this does that. And so this shows that they're inverses of each other. So if we talk about just the logarithmic function, which is the blue part of the graph, if you'll notice the domain, which is our x values, it has a vertical asymptote of 0. That y-axis, the y-axis is the vertical asymptote. So it doesn't cross the y-axis. If you'll notice, it gets really close to the y-axis, but it doesn't cross it. So the domain starts at 0, but 0 is not included, and it goes to positive infinity. So the domain of a logarithmic function starts at 0, 0 is not included, and it goes to infinity. And then the range, it's going down, and then this is raising up, even though it's not raising very quickly. So my range is from negative to positive infinity. Okay, so the domain, again, is all the positive numbers. Okay, it starts at 0 and it goes to positive infinity. So if we were to talk about the domain of just the general logarithmic function, we know that the domain is all positive real numbers, not including 0. So anything greater than 0 is our domain. So if we had a function like this and they were to ask us what the domain is, again, it would be from 0 to infinity with 0 not included. Now, if we had something a little different, like this, and they asked us what the domain of this function is, the way that we figure that out is whatever this is, whatever the argument is, it has to be greater than 0. So to figure that out, we say, well, the argument, this, has to be greater than 0. So if we solve that, that tells us what the domain of this function is. All right, so if I add 5 to both sides to get x by itself, I get x has to be greater than 5. So the domain of this function starts at 5, 5 is not included, and it goes to infinity. So again, take whatever the argument is and say that it has to be greater than 0. Solve that, and that tells you the domain of the function. The common logarithmic function looks like this. F of x is equal to log base 10 of x. But that's not how we write it. That is what the common log is. It's any log with a base of 10. But if our base is 10, the way that we write it is like this. We don't write that base of 10. So if you don't see a base, if you see log and you don't see a base, the understood base is 10. Just like if we have a variable and we don't see an exponent, it's understood to be 1. Or if we have a variable, we don't have a number in front of it, it's understood to be 1. Also, if we have a radical like this, the index is understood to be 2. So we have a lot of understood things in math. So in logarithms, if you see log and an argument, you don't see a base, it's understood to be base 10. Now, we have a couple of logarithms on our calculator, or a couple of logarithmic buttons on our calculator. They couldn't possibly put every base, log base 1, log base 2, log base 3, etc. They couldn't put all of those buttons on a calculator. So there's a couple of logarithmic buttons on a calculator. And so if you look at your calculator and you see the button that says log, then that's log base 10. And it's a very commonly used logarithm. So we're going to look at an example that uses the common log. The percentage of adult height attained by a boy who is X years old can be modeled by this logarithmic function. f of x is equal to 29 plus 48.8 log of x plus 1, where x represents the boy's age and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has the boy attained at age 10? So first of all, before we can plug this in the calculator, we need to replace the variable with a number. So we have 29 plus 48.8 log of x plus 1. Okay, well, it tells us that the x represents the boy's age. Okay, so they want us to find out what percentage of his adult height he's attained at age 10. So we're going to replace the 10 in the function, the x in the function with 10. Which, of course, 10 plus 1 is 11. So this is what we would put in the calculator. All right, if you're using the TI-30XIIS, the way that we would put this in the calculator, you just put it in from left to right, 29 plus 48.8, and then we have a log button. All right, so right here, we see the log button, and just press that, and 11, close your parentheses, and we hit enter, and we get 79.82. Now, if you have the TI-36X Pro, okay, we start out the same way, 29.48.8, and then, let me make this a little bit bigger. We don't have a separate log button, but we have a button that's got ln and log. All right, so it's this button right here. So if you'll notice, it's got two things on the same button. Okay, so if I press it one time, ln comes up. We don't want ln. We'll talk about that in a little bit. We want log. So press it another time, and it changes to log. So you just have to double press your button. All right, and then I put in 11, close my parenthesis. Ooh. Well, let's see what we did. Oh, I didn't put the plus. Okay, so I had put a decimal instead of a plus. Okay, so let me put the plus in there and hit enter, and I get 79.82, which was the same as I got with the other calculator. So we're just going to round to the nearest whole number, and the percentage of adult height that he has attained, since it was 79.8, we're just going to round that to 80%. So he's reached 80% of his adult height at age 10. Now these are the properties of common logarithms. They're the same as the properties that we talked about with the general properties of logarithms. The only thing you have to remember is you have to remember that the base is 10. So if we compare the properties of common logarithms with the properties of the general properties of logarithms, in the general properties of logarithms, if our argument is 1, we know that it has to equal 0. Okay, so it's the same thing with the common logarithm. In the general properties of logarithms, if our base and our argument was the same, then it equaled 1. Okay, so in the common logarithm, if we see that our argument is 10, you just have to remember that the base is understood to be 10. So if those two are the same, then it's going to equal 1. All right, then in the general logarithmic property, if our base and our log are the same, then it equals whatever the exponent is. Okay, so in the common logarithm, we know that it's an understood base of 10. So if the argument is 10, that's going to cancel out, and it's just whatever the exponent is. Okay, and then if we have an exponential function and it's raised to a log of the same base as the base of the exponent, so if these two things are the same, it equals whatever's left. Again, you just have to remember that right there we have an understood base of 10, So if those two things are the same, then it equals whatever's left. So the properties are exactly the same. It's just that in the common logarithms, you have to remember that it has a base of 10. Okay, so we can use that property to help us evaluate some logarithms. So anytime you see a logarithm and the argument can be changed to have the same base as what your logarithm has, or if you can rewrite it as an exponent with the same base, that's going to help you. So since I know that these logarithms are understood to have a base of 10, I can write this. This would be the same as log of 10 squared, because 10 squared is the same thing as 100, right? Okay, so now that understood base of 10 and my argument are the same, so that's going to cancel out, and that equals 2. Okay, so if I have log of 1,000, well, I can rewrite 1,000 as 10 to the third power. So now that's a common logarithm, so we know my base is understood to be 10 and my argument's 10, so that cancels out and it just equals 3. In this last one, it's already written as with a base of 10 raised to the 7.1 power, so since my understood base is 10, that part cancels out and it just equals whatever the exponent is, 7.1. Okay, so I told you that we have a couple of buttons on our calculator that represent logs with a certain base. Okay, so we just talked about common logarithms that have log base 10, and that's written as just log with no base. The other logarithm that's on our calculators is the natural logarithm. Okay, so the natural logarithmic function is f of x is equal to log base e of x. Well, we can't just write this as log of x, because if we don't see the base, it's understood to be base 10. So the way that the natural logarithm is written is f of x is equal to ln of x. Okay, so ln stands for natural logarithm, and I realize that that's not, that would be nl instead of ln. Well, the reason why it's written like this is because it's derived from the Latin form, which is something like logarithmic, or actually it's Logarithmus naturalis. So it's derived from the Latin form, so that's why it's written like that. But we have a button in our calculator, an LN button, and that stands for natural logarithm. So that's the other logarithm that we can just plug into our calculator. All right, so the natural logarithm has the same type of graph as a regular logarithm. Any logarithmic function, whatever the base is going to have the same domain as what we talked about earlier, because it's a logarithm. So because of that, natural logarithms also have to have a domain that's positive. So since this says find the domain of each function, remember all we have to do is say that has to be greater than 0. So if I write that out as 4 minus x needs to be greater than 0, to solve this, I would subtract 4 from both sides, and I have negative x is greater than negative 4. Okay, so then I need to divide by negative 1, but since this is an inequality, anytime I divide by a negative, I flip the inequality. All right, so the domain of this logarithmic function has to be less than 4, which might not make sense because we're saying we know that it's got to be greater than 0, but let's test it out. If I were to plug in a number that's less than 4, say if I were to plug in 0, well, 4 minus 0 is just 4. Okay, so that's greater than 0. All right, so let's go the other way. If I were to plug in something greater than 4, so that should not be in the domain, okay, because it's saying x has to be something less than 4. So if I plugged in 5, 4 minus 5, that would give me a negative 1. It can't be negative. It's got to be greater than 0. So this does work out. So my domain, the domain of this logarithmic function has got to be less than 4, so that means it's from negative infinity to 4, and 4 is not included. So that's the domain of this function. Okay, so then for the next one, h of x is equal to the natural log of x squared. They're saying, okay, what could we plug in for x that would still be in the domain? Well, of course, if I plugged in any positive number squared is going to stay positive. And then any negative number, if I square a negative number, it's going to be positive also. But if I square 0, it stays 0. Okay, so remember, for the domain of the function, whatever the argument is has to be greater than 0. So if I plugged in a negative number, it turns to positive. If I plug in a positive number, it stays positive. But it can't be 0 because if I plugged in 0, 0 stays 0. So my domain of this function is just all real numbers except 0. Or if I wanted to write it as an interval, I could say from negative infinity to 0, 0 is not included, unioned with 0 to infinity. All right, the properties of natural logarithms are the same as the properties of the general properties of logarithms. Again, we just have to remember that our base is e instead of something that's written. So just like the common logarithm, if my argument is 1 in the natural logarithm, if my argument is 1, it equals 0. Then if my base and my argument are the same, it equals 1. Okay, so here we don't see the base, but we know if it's ln, the base is e. So if my argument is e, it's going to equal 1. Or if I have some exponent, it's going to cancel out and equal whatever the exponent is, just like in the general logarithmic properties. And then here we have e to the ln of x power. Well, that ln we know has an understood base of e, so that part cancels out and it just equals what's left, which is x. So it's the same properties again as the general properties. All right, so when the air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x is equal to 13.4 ln of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. So it's saying that x are the number of minutes, and so they want us to find out what the temperature is after 30 minutes. So all we're going to do is plug that into the function. So we have 13.4 ln of 30 minus 11.6. Okay, so now we're going to plug that into the calculator. I'm not going to go through typing in the whole thing, but I just want to show you where the buttons are on the calculator. All right, so on this TI-30XIIS, you have a button that says LN. It's right underneath the log button, so that's the button you would use. And on the TI-36X Pro, remember it's the same button as the logarithmic button, so this time you would just press it one time and you would get to the natural log. So for either calculator, if you plug that in, you should get 33.97. Well, it says to they want it to the nearest degree, so that would round to 34 degrees for your answer.